Look at this calculation. 1/3 plus 1/4 equals 2/7. You add the top numbers, you add the bottom numbers. It looks perfectly logical, and it's the most common mistake students and adults make with fractions. Or take comparison. Ask someone to look at 1/8 and 1/3 and identify the larger quantity. A significant percentage of people will point to 1/8, simply because 8 is a larger number than 3. Human cognition is wired for whole numbers. We count distinct, unbroken items. So when we look at a fraction, our brains naturally process it as two separate whole numbers stacked on top of each other. We try to bridge this cognitive gap with memorization. We learn procedures to manipulate the numbers on the page, but under pressure, those memorized rules degrade, and we fall back on whole number logic. The word fraction is derived from the Latin root fractus, meaning broken. Fractions were invented to describe the physical reality of broken things. Treating fractions like stacked whole numbers misreads that physical reality. To understand the numbers, we have to translate them back into physical shapes. Look at this diagram. The bottom number, the denominator, is a structural blueprint dictating exactly how many equal pieces a whole object was cut into. The numerator is an inventory, a raw count of how many blueprint pieces you actually possess. If your inventory count is lower than the total cuts, you have a proper fraction, less than one complete whole. If your inventory exceeds the blueprint, you have an improper fraction. You possess enough pieces to fill one whole, spilling into a new shape. When you view fractions as physical objects, comparison is immediate. A slice taken from an object cut into 8 pieces is visibly smaller than a slice from an object cut into only 3. Mathematical concepts like finding equivalent fractions or cross-multiplying are shortcuts. They allow us to easily compare these different slices without having to draw them out every single time. Comparing fractions relies on accurately visualizing the physical mass those numbers represent, rather than looking for the highest digit on the page. A third slice and a quarter slice fail to form a uniform grid. You cannot add pieces of different sizes. Finding a lowest common multiple recuts the mismatched pieces into a smaller, uniform size. Once the pieces match, you combine and count the total. Multiplication carries its own set of assumptions. We are conditioned by whole numbers to expect that multiplying two numbers always produces a larger quantity. We map out multiplication with an area model. Divide a square vertically for the first fraction, then crosshatch horizontally for the multiplier. Multiplying fractions physically means taking a part of a part. The resulting intersecting area is smaller than the starting fractions. Mathematical operations are shorthand notation for the physical manipulation of matter. Let's look back at the equations from earlier, this time translating the digits into physical shapes. The rules that dictate finding common denominators, converting mixed fractions, and multiplying straight across all align perfectly with how you would physically move those pieces on a table. When someone incorrectly cancels numbers across an addition problem or adds the denominators together, it provides a highly specific diagnostic signal. It points to a gap in visual understanding, not a lack of mathematical ability. Blind rule following is fragile. It requires perfect recall of abstract procedures. Visual comprehension is permanent because it relies on observing how actual objects behave. Mathematics is a descriptive language. The rules exist to accurately record physical reality. Once we stop trying to memorize the grammar of equations and start visualizing the physical reality they describe, mathematics stops being a memory test and becomes a powerful tool for making sense of the world.